Hello, everyone. Good morning. Welcome to another HSMA session. I hope you all had a good break, study week last week. Certainly looking at the Slack, looks like lots of you had a bit of a get together and sort of did some revisions. Hopefully that was really useful. We swing back this week into two different sessions today. This morning I'm going to be taking you through the final part of Module 2, the Discrete Event Simulation module. And we're going to be looking at some things in SimPy so last time obviously we introduced discrete event simulation, and we had a look at how we can build discrete event simulation models and the basic structure of them. But today we're going to look at some extra little things that you may want to include depending on what you're wanting to do. And there's lots of other things that we will that you may want to include in your model. So we can't cover everything. Sammy in her reference book, the DES, Little Book of DES, that's got some other things that we don't cover here today as well. So do use that, because it's an excellent reference material. But there'll even be things in that that aren't covered in that. But hopefully by the end of today, you'll have a sense about how SimPy works, how you might be able to build these things in. And then, the beauty of any of these approaches is that, they're based around Python, and so you can pretty much do anything. But we've decided to focus this morning's session on things that you may well encounter when you're trying to build your own discrete event simulation models that will hopefully be useful. And there'll be lots of chance for you to practice building discrete event simulation models this morning as well. And then you'll be pleased to know that you will have a break from my voice this afternoon as Sammy takes over for Module 3 and introduces you to the geographic modeling module. So let's kick off this morning. So last time, as I say, we looked at the kind of basic structure of SimPy. We looked at how we would put together a SimPy model in an object-oriented format, and we looked at how we would structure that, and also how we would gradually kind of build it up piece by piece. And you actually built your very first discrete event simulation model, a relatively simple model, but one hopefully that you could see, well, actually I could build models like this of my own pathways. But as I said, there will be aspects that you will encounter in your real world systems that you may well want to capture. So this morning's session is kind of an extra bells and whistles session combined with a bit more practice on SimPy. Now, something to flag up is that the examples I'm going to show you this morning of these extra features, I'm basing it around very, very simple models. So most of the examples, I'm just using the very simple first model we looked at, which was, patient comes in, sees nurse, leaves. But obviously, everything I'm showing you applies to any model that you build, regardless of complexity. But just to keep it simple for this tutorial, we're just showing you based on the simplest possible model for most of the examples. Okay, so you'll remember at the end of the last session, your exercise was to build a model of a GP surgery, and you had patients who were coming in, and then you had some of them were booking tests, and then you had simultaneously you had a receptionist who was registering them and booking tests, and also taking phone calls that were coming in. Now that system that we were creating of a GP surgery is a system in which patients will come into the surgery and the service opens, and then they leave when it closes. Okay, and some of the systems that you are modeling will follow that pattern. But what if your system that you're trying to model isn't like that? What if we've got a system, for example, an emergency department, that is never empty? Okay, so we don't have empty emergency departments. Now, there's a slight problem if we've got a system like that, and there'll be lots of healthcare systems that are like that, that they are never empty, because by default, whenever you start to run a discrete event simulation, you start from empty at the start of the run. But if we were, say, modelling an emergency department, that's going to throw off the results, because that means that at the start of our simulation, the model is empty. There are no queues. The first patient that comes through, at the very least, is going to have no queuing whatsoever and will fly through the system. And indeed, depending on the scale of any problem in your system, it may take a while for any true queues to emerge, and you will have an initial period where actually everything's running pretty okay and people aren't waiting too long. Now that's probably, if you're modelling something like an emergency department, not going to be representative. And depending on how long you're running your model for, that can throw off your results to a lesser or greater degree. And this is a problem in discrete event simulation known as initialization bias, which is where we are capturing a real-world system that is not empty, but we are starting our model as though the system is empty, and that is skewing our results. Fortunately, because this is a known problem, there is a known solution. And what we do in discrete event simulation is we use something known as a warm-up period. Now, basically, a warm-up period is a pretty simple idea. The idea is that you run your model as normal, as you've already seen, from empty, so it starts empty, and you run it like that. But for a certain period of time, which we call the warm-up period, we don't collect any results. Okay, so we just let the model run, we let it do its thing, but we don't collect any results during that warm-up period. Now, the amount of time that you set as being the warm-up period is entirely up to you to define, and how you arrive at how long that warm-up period should be is again up to you. Now, you can be very, very precise about how you try and work out what your warm-up period should be. You can use statistical testing to try and identify when your system reaches an equilibrium state. I've put in a little link here which talks through a little example of how you might approach that. Or you can just kind of plot what's happening over time by eye, look at your queues over time, and sort of get a feel for when it might be a good time to start the results collection period. Or you could just set it to a really long warm-up period so that you know that will be long enough. That's a little bit of a my personal approach is I tend to go for the second one. If you just set a really long warm-up period, you could, if you've got a very complex model, you could end up creating something that's very inefficient, because you're running your model for too long a period and not collecting any results, and that's not very, very efficient. But there's different ways you can approach that, and you can be as kind of precise about it as you want to be, and it depends on what you're wanting to do with your model. But the key thing is that you have this warm-up period so that the model runs as normal, but you're not collecting results until that warm-up period has expired. And that prevents that initialization bias, because then when the results collection starts, it's starting from a non-empty system. Now, the good news is that it's really, really easy to implement a warm-up period in SimPy. All we have to do is check the current simulation time, which you're already used to doing, because if you remember from your SimPy models, when we calculate the how long the patient's been queuing, we record the time when they enter the queue and the time when they left the queue, and then take the difference. We use that same give me the time now command to basically work out what the current simulation time is and see if we're in the warm-up period. And if we are, we don't collect the results, and if we're not, we do. And it really is as simple as that. So we're going to look at a little example of this. So in the lecture examples, we've got the warm-up example.py file, so you can check that out yourself. I'm going to bring up the code in a second. As I say, this is a very slightly amended version of this simplest model that we looked at initially, where patient arrives, they come in for a nurse consultation, which needs a nurse, and then they leave. And that was the very first model we looked at. I've made some minor tweaks to that model. It runs for a longer duration. There's a few more runs, and there's a little bit of an added calculation in the trial results. But it's basically that kind of simple model. But crucially for this, I've added a warm-up period to that initial model. So we're going to assume that this system is actually a 24-hour system. So maybe it's representing a triage at an emergency department, for example. So that this system is never empty. It runs 24 hours, and there are always patients that potentially are coming in. So as before, I've marked kind of new bits that are new for this putting in a warm-up period bit with this hashtag new in the comments, so you can see what the bits I've added are to get to this warm-up period. So let me bring up this file. I'll very briefly, just first of all, just remind you of how the models are structured. Hopefully this is you remember most of this, but I'll just a little refresher. So we've basically got 4 classes. The first class is G. That stores our kind of global level parameter values, things like your average inter-arrival times, average activity times, how many resources of each type you've got, how long you want to run the model for, that kind of stuff. That all goes in class G, and it's a special kind of class that we don't create an instance of it, we just refer to it directly. Then we have a class for our entity. Obviously, if we have more than one entity, then we need more than one class for this, but we've only got one here, patients. Within that, we have any attributes within the constructor that are set up that the patient will need to carry with them. So here we've just got the patient carries with them their ID, so we can identify particular patients, and they'll carry with them information about the queuing time for the nurse, how long they spent queuing for the nurse, which starts at 0, and then basically when they queue for the nurse, after they've queued, they then make a little note of how long they've queued for, and we can access that. And then we've got the model class, which is basically where all the magic happens, with the constructor set up, which sets up basically the environment and the resources we need, what the run number is, sets up the data frame to store the results from that particular run, and all that kind of stuff. And then we've got a generator function that represents an arrival point, a DES generator. So we've only got one arrival point in our model. It's just patients coming in to see the nurse. And that generator function, remember, generator functions are just like normal Python functions, except that when we pass control back, when we then run that generator function again, it starts from the point it left off. So basically an arrival generator here will increment the patient counter. It'll create a new patient of the patient class that we set up above. It'll then chuck them through the other generator function that's down here, which represents their journey through the clinic. It'll then sample from an exponential distribution the inter-arrival time until the next patient, and then it'll time out. It'll freeze in place until that point, and then when controllers pass back, it'll increment the patient counter and create the next patient and chuck them through the pathway. And then this is the pathway here. We've only got a very simple pathway. They just come in and see a nurse. That's all they do. That patient will basically start queuing for the nurse. They'll request a nurse resource, and then they'll freeze in place until that request can be met. Once it has been met, then we record that they've stopped queuing for the nurse, and we can calculate the queuing time, and the patient can make a little note of it in their attributes. Then I'll come back to this bit, and then we basically randomly sample how long they spent with the nurse, and we freeze in place with the nurse, and that represents the activity time. And then and that's basically the main bulk of how the model works, but we've got other stuff. Like we've got a method to calculate the results from that particular run, a method to run a single run of the simulation, which will start up the arrival generator, and tell the simulation to run for the amount of time we want it to, and then calculate the results after that particular run. And then we've got the final class, which is for a trial. And that basically, remember, a trial is just a batch of runs, because we don't run a simulation just once. We run it, if it's a stochastic simulation like this, because there's an element of randomness, we run it lots of times and take average results over that batch of runs, which is called a trial. And so this class just defines that for us. It sets up a data frame that will store the trial level results. it'll calculate the. We've got a method to calculate the averages over that trial, to print the results over that trial, and to run a trial, run a batch of runs, and then in order to kick all this off, all we have to do is create a new trial and run the trial, and then it'll set in motion all that chain of events. So that's just a very quick whistle-stop reminder of how these things are structured. That's a basic structure of a kind of an object-oriented SimPy model. So let's have a look at the. We've already seen this this simple model. I want to now add in a warm-up period. I don't want my system to record results where it's starting from empty. So I'm just going to do a search on the hashtag, and that will automatically highlight the new bits I've added. So the first new thing that you will see that I've added to put in a warm-up period is I've added a global level parameter here, which is my warm-up period. Now remember, this is in time units, and in this model, my time units represent minutes. So we can see here that the simulation will run for 2,880 minutes, which is 2 days, 48 hours, and it'll do 100 runs. I want to specify that before it does this, I want to have a warm-up period of 1440 minutes, i.e. 24 hours. So the system, I want it to run, the model to run for a day's worth, 24 hours worth of activity before it then runs for a further 2 days where I start collecting the results. So I'm giving it 24 hours essentially to warm up. So all of this down here will remain exactly the same. The key change is going to be down here where we have essentially the patient pathway. And this is where we start adding results. And this is obviously where we need to change things. So you remember whenever we have a patient that queues and then they finish queuing, we calculate how long they were queuing, and then before we were just doing this, so this line of code was exactly the same as it was before, which basically says, okay, well then record this patient's ID against the queue time, how long they spent queuing for the nurse, put it in that particular column, and that's what we did before. We're doing exactly that thing again. The only difference here is that we will now only do this if we're not in the warm-up period, okay? And it literally is as simple as just putting this in an if statement. So here we've just said, before we do this, let's just check we're not in the warm-up period. So we can call the now attribute of the environment, the SimPy environment. That the SimPy environment is stored within the model class, and we are in the model class here. So we say, my model, its SimPy environment, give me the time, the simulation time now, exactly as we do for calculating the current time for the start and the end of the queue. Check if that current time, that current simulation time, is greater than the warm-up period that I've got stored in the G class. So in this case, if the simulation time has gone past 1440, if it has, then you can record this result. If it hasn't, don't do anything. So the patient will still come in, it will still queue for the nurse, it will still use the nurse resource, but the results will not be recorded. Okay, so it's allowing the system to warm up. That's the whole point. So that's the main change that we have to make. But there's a couple of extra little things that that we'll need to do for our particular way. We've got things structured as well. So there's a couple of minor tweaks. So for example, here the way we've set up a data frame, and there's, again, there is no single right answer. This is just the way I do it. So you'll remember when we set up the data frame for collecting the run results, we set in the first row basically, and before what would happen is then the first patient would come in and it would overwrite the results of that first row. But that's now not going to happen because now we've got a warm-up period, and so the first patient that's recorded will not be patient 1. it'll have an ID that's much higher because it's already had loads of patients come through that just weren't recorded in the results. So the way I'm doing it, just to it will make a slight change to your results. The scale of that will depend on how long you run your model for. So if this ran for ages, that first patient having a 0 queuing time won't make much difference. But it's good practice to eliminate it because it's a dummy entry. So I'm just dropping that first row basically. So get rid of that first row. That's not gonna count now. That's one way of doing it. The other way you could do it, you could, if you so chose, start the IDs from the point at which you have it coming, have them coming out the other side of the warm-up period, but that can be a little bit more complicated. So I just tend to do this, just remove that first row, that dummy patient that will never be used. So I need to add that in. The other thing I need to tweak down here in the run method of the model is I need to, whereas before we told it to run until g.sim duration, now I need to tell it to run until g.sim duration plus g.warmup period. In other words, I need this model to run for the warm-up period plus the amount of time. So 1 day's warm-up plus 2 days of results collection. Okay, so you need to make sure you do that. Otherwise, if you forgot to do this bit, then you will end up with a simulation where you are not collecting the results for the first day, and then you're only running it for a day. So do remember to add that bit in. Other than that, that's it. So basically all I've had to do is specify a warm-up period in my global parameters. Then whenever I add results, I check first that it's outside of the warm-up period before I do that. I drop off that first row in the run results, and I need to remember to run the simulation for the period I want plus the warm-up period, and that's it. That's all you have to do. In fact, so if let me move this bar first of all, because that's right in the way. Let's click OK on that. So let me run this model just so you can see it, and you'll see. In fact, I'll run it 2 different ways. So let's run it with the warm-up period first and see what happens. So there we go. So we've got if you remember this, we indicated that there's probably going to be an issue in this system because on average, let's have a look back at the result, at the global parameters. We've got patients on average arriving about every 5 minutes, but on average they're spending about 6 minutes with a nurse. So patients are on average arriving a little bit more frequently than the nurse can deal with them. Only a little bit, but there does seem to be a problem with that. That indicates there will be an issue, and indeed, we see the scale of the issue here. So by running it for 2 days after a warm-up period, we find that the mean queuing time for the nurse is 501 minutes. Now let me take out that warm-up period, and I can literally just put 0 there, and I'll run that again. Oh, sorry, the zoom bar is really annoying. We should get rid of this. There we go. Let's run that again. Oh no, I've done that wrong. Sorry, just give it a second. And then here, right, now look at the scale of the difference. So by just running it without a warm-up period, it's about half the waiting time. So it's still high, and it still indicates there's a problem, but we've just run it for 2 days with no warm-up period, but at the start, the system was empty, and that's that initialization bias has caused our results to be skewed, because what it's actually then indicated is, well, everything was fine initially, and so that's then brought down that average. And so that's why we've got a much lower result. So that's the scale at which your results could be affected if you don't use an appropriate warm-up period. And indeed, this may not be the right warm-up period for the particular system that we're modelling. I'm just using this as an example. But hopefully that shows you the kind of the potential scale of that. Okay, I'm wondering if it might be worth me just checking after each one if there are any questions. Sammy, are there any questions cropped up about warm-up periods?
So we had a quick discussion about instead of warm-up periods, could you actually have a defined start point So I think the answer to that is yes. In some cases, if you've got a very specific position where you're trying to model how you could get away from a particular baseline point, see how long it would take to clear a particular backlog, that sort of thing.
Yeah.
And I think there was also a question about whether you could store the warm-up period to remove the need to run it every time. My feeling on that is that there probably isn't much of a speed benefit to be gained from that, and actually you probably want that variability that you will see in the warm-up period across different warm-ups.
Yeah, 100%. And yeah, regarding the first question, yes, you can pre-populate, and there'd be different ways in which you could do that depending on what you're wanting to do. But you probably have, if you're doing it in a Pythonic way, and making sure it was object oriented, you probably want some sort of, maybe even a separate class, but certainly a method within the model class that would basically run a warm-up period and get it to a specific point to pre-populate, so like a pre-populate method to set up your system so that it looks like this at the start. So yes, you could do it. The key thing is the key question you need to ask yourself is, do I need a warm-up period for this model? And the answer is yes, if your system does not start from empty. So if you're building a model of a GP surgery and you're modeling a day in the life of a GP surgery, and patients come in at the start and then they're all gone at the end, doesn't matter. You don't need a warm-up period because it starts from empty. But if you've got a system where that is not true, then you do need a warm-up period. Cool. Okay. In which case, we will move on to the next topic, which is priority-based queuing. So we touched on this a little bit in the previous session, and I mentioned this might be quite important for a lot of your models. So far, when we've built our models, we've assumed that our models follow a FIFO, a first in, first out policy. In other words, whoever's queued the longest is seen next. But of course, in healthcare systems, that's not very often. That's not the only way in which patients are seen. In fact, there would be a level of prioritization that would be involved. You don't have somebody that's come in, say, with a cardiac arrest, and somebody that's got a broken leg, and say, well, the person with the broken leg was here first. We'll have to deal with them. You have a level of prioritization. Okay, and that's typically linked to something about the severity of the patient's condition. Now, the good news is that we can really easily build in priority-based queuing into our SimPy models using something known as a priority resource. There's an extra class in SimPy that allows us to do this really easily. And basically, a priority resource is just like the resource class that you've already used. So when we set up a nurse, we say it's of type resource within the SimPy package. They have a resource class that defines what a resource is in a discrete event simulation. Rather than have one of those, we have a priority resource instead. And basically, it's identical to a standard resource class. It just has this extra functionality that allows it to choose who to take out of a queue based on some sort of priority. Okay. And the way this basically works in SimPy is we set up the resources, any resources that will be dealing with a priority-based queue, we set them up as priority resources rather than resources. Okay, so you don't need to do it for if your resource will never be dealing with any priority queues, you can just keep them as standard resources. But if they are potentially going to be prioritizing, you just set them up as a priority resource instead. Then we have some sort of attribute that will be stored against the entity. So in our case, a patient, that will basically specify and define that patient's priority. Now, the crucial thing to note here is that can be anything you like. It has to be a numerical value though, and the way a priority resource will work is that a lower value indicates a higher priority. So you must remember that. You can't do anything about that. That's how it's set. Whatever your attribute is, if your value, you've got somebody with a value of 1 and somebody with a value of 5, the value of 1 would get higher priority. Okay, so you just need to remember it's that way round. So that can be easy to forget. It kind of makes sense if you think about it. If you think about like a priority 1 patient, you would imagine they would be higher. So we set up the resources as priority resources, any that are dealing with priority queues. We have some sort of attribute stored against the entity patient in this case that will indicate their priority. And then the only other thing we have to do is when we request a priority resource, so like we did before where we say, I need to request a nurse now, if that nurse is now a priority resource, we also have to say, oh, and by the way, this is the attribute of the patient I want you to look at to determine their priority. Okay, but basically that's it. That's all we have to do to build in a priority queue system into a model. Now, the example I'm going to show you now is just based on a patient having a single priority attribute. Depending on the complexity of your model, you may have something where you have different attributes for different priority levels for different queues. You could potentially have that. It's the same principle. Okay, it works exactly the same. But just to keep it simple initially, let's just imagine a single priority bit. So let's have a look at priority resource example.py. So the next example here, again, I'm not going to go through all the code. It's all exactly the same as before. The only bits that I've changed are the from the previous example are the bits that are tagged new. So each of these will build up piece by piece so that we add in extra bits to the previous model that we've looked at. So here in the G class, but this you don't have to do. This is just for me to show you to make it a bit clearer when I'm demonstrating this. I've basically just shortened the simulation duration and put in so that it's a single run. This is just to show you what's happening with the priority queues. You wouldn't do this in reality. This is just to make it easier when I demonstrate it to you, so you can actually see how it works. But I just wanted to flag that up. That's changed. So here in the patient class, before we just had ID and some record attribute where they'd store how long they queued. I've added this extra attribute of a patient. I've just called it priority. If you've got more than one, or it's for different queues, then you may want to rename that something a little bit more useful, but I've just called it priority. And you can set that to whatever you like. It just has to be a number. That's all. All it has to be. It doesn't even. I don't think it even has to be an integer, as far as I know. But I'm using integers here. And basically, all I've done here is I'm just gonna, when I create a new patient, this is the constructor, remember, so it'll run this bit. I'm just telling it to randomly pick a number between 1 and 5 and make that the patient's priority. Now, in reality, you probably wouldn't do that. You'd probably want some way of determining each patient's priority. Unlikely, you'd probably say, well, 30% of my patients are priority 1, 40% are priority 2, and you'd have a little if statement here that would then allocate that out. Okay, you can do whatever you like, but you ultimately need a variable stored against the patient class, in other words, an attribute that stores a number. And that's what you need. So I'm just randomly generating a number between 1 and 5, but you can do it however you like. This is just for simplicity. So our patients, if we run enough of these through, about 20% of them should be priority 1, 20% priority 2, etc. Because I'm just randomly picking from a uniform distribution here. So then when I create the resource, set up the resources in my model constructor, before we said self.nurse equals simpy.resource, and we said this is the environment you'll live in, and this is how many nurses I want. This is identical. The only difference is rather than saying simpy.resource, I've said simpy.priority resource. So I'm going to create a priority resource for the nurse rather than it just being a resource. Okay, that's the only difference. Scroll down. Then when we get down to the attend clinic, this is the pathway bit. I've added in some print messages here. Again, if you were doing a real model, you probably wouldn't do this. I'm literally flagging up anything that I've added. That doesn't necessarily mean you'd need to add it if you wanted to add a priority resource, but I'm just flagging up what's changed. So here I've just basically added a print message so you can see how the priority works. It's probably a useful thing to do for your own models initially to check that things are working. Helps you validate your model. But basically I'm just going to print a message saying this patient with this priority is now queuing for the nurse, and similarly down here when they're being seen, so we can have a look to see if the priority system seems to be working. But those little extras, really. The key change here is when we request the nurse, we request it exactly the same as before. The only difference is that where we said self.nurse.request before, we just opened and closed some brackets and we didn't put anything in them. This time, we are putting something in the brackets. And the thing we're putting in is priority equals patient.priority. So this is basically telling the nurse, this is how I want you to determine the priority of the entities that are coming into you. Okay, so the way in which you assess priority is via the priority attribute of the patient I'm giving you. Okay, because we're in the model class, remember, so a patient will be given over to an instance of the instance of that model class at the instance of this generator function representing this patient's journey through the clinic, and we say grab that patient's priority. So whatever that patient was randomly allocated, the number between 1 and 5, that's the number that this nurse is going to look at. Okay. Scroll down and there's nothing else. Okay, so basically, if you ignore the fact that I've added in a couple of print messages and shortened the runtime just to make it a bit easier for when I show you this, there's barely any change that I've had to do. I've literally just put in some sort of priority attribute and some way of defining what each patient's priority will be. Then I've set up my resource as a priority resource instead of a standard resource. And then when we request that resource, I tell it what the priority attribute is that they need to look at. That's it. That's all you have to do. That will then give you priority queuing. And if you don't believe me, let's now run the simulation. So if I click run, let's give it a second. This will run very quickly because I've only got one single run and it's much shorter. So we've got the results down here, but which will be much lower because we're only running it for 2 hours. Let me just scroll up though, because this is the bit I'm interested in. So here we see these are my print messages, so I can see what was happening. So patient 1 came in, they had a priority of 4. They were then seen straight away because obviously there was no queue, it was empty at the start. Then patient 2 came in and they were seen. Now this is where it starts to get a bit more interesting. So then, whilst patient 2 is being seen, patients 3, 4, 5, and 6 all came in and started queuing for the nurse, okay? But they've got different priorities. So patients 3 and 4 have got priority 1, patient 5 has got priority 5, and patient 6 has got priority 3. So 3 and 4 should be seen first, then patient 6, and then patient 5, unless somebody else then comes in before patient 6 is seen with a higher priority, or a lower number if you like. Okay, so we see patient 3 is then seen by the nurse. We then get another patient with the top priority that's come in. Okay, so we've got patient 3 is being seen, then patient 4 is seen. Those are the 2 that came in first with priority 1. Then we've got another patient, in fact, that comes in with priority 1. And then that patient is then seen. So they jump. Sorry, I've skipped down. My eyes are now blurring. So patient 3 is seen. No, that is right. So it is taken. That's weird. Sammy, are you looking at this? It's taken the most recent patient with priority 1, so it hasn't done a FIFO. I'll need to look into that. I thought it broke ties with a FIFO.
I thought that too. So yeah, I will also look into that. Sorry, I was keeping up with the chat, so I was not following quite there.
No, that's okay. I don't know. Oh, hang on. Sorry, patient 7 is seen. I think it's my eyes. I can't. I can't read this as well as I thought. Sorry. I think patient 7 is seen first. Patient 7 comes in. They've got a higher. So 3 and 4 are seen. 5 and 6 come in at the same time as 3 and 4, but they've got pretty low priorities. Patient 3 is seen, which is correct. Patient 7 then starts coming in. They've got a higher priority than 5 and 6. 4 is seen next. That's correct because 3 and 4 came in with high priority. Sorry, it is correct. It's just I can't see what I've done. Then patient 7 is seen. So patient 7 here, who came in after patients 5 and 6, but is seen before them because they came in with a higher priority. Sorry, well, it was correct. I was just I thought that was odd because it usually works. So we can see here that the system is working. That we are not, and it does break ties with FIFO. So patients 3 and 4, who both came in, 3 and 4 came in. Sorry, patient 3 came in first. Patient 4 came in second. They've got an identical priority, so therefore they are seen in the order in which they came in. So patient 3 was seen first, then patient 4. But 5 and 6 had to wait longer because this extra patient, before they could be seen, came in who was a higher priority than them. Hopefully that makes sense. Sorry, I probably absolutely confused you there, but it is exactly what I said in the first place. I just confused myself. Any questions that have come up about that, Sammy?
So a couple of related ones. So we've got, can you do something to stop the broken leg patients waiting for years because there are cardiac patients coming in all the time? And related to that, can you have a dynamically changing priority in some way? Can someone, if they've waited a long time, could their priority potentially creep up or down, depending on, is this something we could build in?
Yeah, absolutely. I mean, you can do anything you like. So that, remember, that priority is just an attribute of the patient. So you could do something like really really clever, where you said every so many time units of the model, that priority level goes down by a certain amount. And you could do something like that. But remember, you're modeling a real world system, so you need some sort of data or to back that up, or some sort of expert opinion to say, yeah, it's going to be, if somebody was waiting there an hour, we'd bump them up or something like that, that would then justify that assumption that you're making in your model. But yes, you can do anything you like. You can have it dynamic. You can have a fail safe, so that you don't have a patient that's just never seen because higher priority patients keep coming in. But again, the way you deal with that is to ask the stakeholder and say, well, how does that work then? What stops in the real world system? What stops somebody with a broken leg never being seen because they're a higher priority ones? What happens? And then that's how you would model it. So hopefully that makes sense.
Yeah, that's great. Another one that came up is could you have a dictionary to have a priority value and link it to conditions, so you could create some sort of ratio perhaps of how often different priorities occur? That sounded like a nice idea actually. So,
Yeah, definitely, that would be really cool.
and the other one was, is there a way potentially, I think we might, I'm not sure of this off the top of my head, but is there a way to basically make it not break the ties with first in, first out? Is there, I suppose, having an additional attribute or something that affects the priority in some other way? You might need you might still have to have additional levels of priority or something like that, have additional granularity to your priority to make that work, I think.
Yeah, I
Um,
think.
yeah, lots coming in. Or yeah, so could you bump the patient up priority if they exceed a certain time? Yep, absolutely. I believe that would definitely be possible. And can you work on a percentage time weighted against expected? I just trying to work that one out. I think that would work. So actually, if you've come up, yeah, I suppose if you're saying that you would expect them to wait 4 hours and they've waited 3.5 at this point, you could start bumping up the priority. That would
Oh, I see.
absolutely
Yeah,
work. So
yeah, yeah.
yeah,
For
lots of, as Dan says, so much flexibility. That's the wonderful part about SimPy. If you think you might need to do something in your model, you probably can.
Yeah, absolutely. I mean, this gets to the heart of why we use a Python approach, because Python allows you to do absolutely anything. You are in Python, so it doesn't matter. There's certain things that are built into SimPy, like priority resource, but you can build anything you like around that. You could, if you so chose, you could have a machine learning model bolted onto your priority to learn and predict what priority. I mean, don't do that; it's going to be complicated. But you could. There's nothing stopping you doing that. You can do anything you like, and that's the kind of key takeaway from it. Anything you can imagine, you can do it. There are certain sort of standard things that SimPy can do out of the box, that are like this, but you can bolt onto that whatever you like, whatever logic you want. But just make sure anything you do is kind of grounded in reality, that you are doing something that is based on how the real world system works, or some sort of approximation, a reasonable approximation of it. Because it could affect your results if you just start. it's very easy when you're model building to start getting into making things up. And I know it sounds, oh, I'd never do that. You can very easily get into that habit if you're not careful. So, oh yeah, well, we'll have this system. That sounds reasonable in my head, but always check with the stakeholders: is this reasonable? Is this how it would work in the real world? Okay, I'll move us on because I'm conscious I'm going well over time, but hopefully this is useful to start to see some of these things. Next thing I'm going to talk about is resource unavailability. So far in our models, we've basically assumed that other than the stuff that they're doing in the model, our resources that are in the model are always available for the amount of time that we are simulating. But of course, that's not always going to be the case in the real world. We may have resources that are not always on shift, and this commonly happens where you're modeling. Okay, we're modeling a nurse that's doing this and this, but we're not creating a model of the entire hospital, and so the nurse may be off doing this at certain times as well. Something that we're not capturing in our model, and we don't want to have to. If we think back to our initial session, we don't want to have to model everything. We don't want to model all the stuff the nurse does. But we need some way of being able to say the nurse isn't always available, the doctor's not always available, whatever it may be. And the way in which we deal with resource unavailability basically boils down to this question. It's the first question you should ask yourself. When these things happen, either a doctor or the resource goes off shift, or they're off doing something else, does another resource of the same type cover? If the answer is yes, then it doesn't matter. You don't need to worry about it. It doesn't matter that your model says there are 2 doctors at all times. It doesn't matter. They don't have to be the same doctor, as long as it's true that there are 2 doctors available at all times. Or for, I mean, they might go to the loo. You don't need to get down to that level of detail, but you know what I mean. So if that's the case, if the level of cover for that resource is always the same, you don't need to worry about it. Or it's always the same for the particular time period that you're modelling, then you don't need to worry. Where you need to worry is if sometimes the doctor in your clinic gets called away and there's no doctor for 20 minutes. That's where you need to start modelling that kind of stuff. Okay. So if that is the case, and you need to model resource unavailability in some way, the way we can do this in SimPy is a little bit of a fudge, but it makes sense if we think about it. We can do this by simply obstructing a resource for a certain amount of time. So let's think about our simple model here, where we've got patient arriving, they come and see the nurse, and then the patient departs. And let's imagine that every 2 hours, our nurse has a 15-minute break, and there's no nurse that comes in to replace that nurse. That we are 1 nurse down, and if we've only got 1 nurse, we have no nurse essentially for 15 minutes. So let's see how we've modelled that. The way we do this is to have our model just as we did before, but we'd also have this second generator here that its sole purpose is every 2 hours it would request the nurse with the highest priority, higher than any of the patients coming in, and it will keep that nurse for 15 minutes, and that will represent them being unavailable for an amount of time. Okay, so to do that in SimPy, we basically just set up the frequency and duration of unavailability as our parameter values in our G class. So how often will our resource need to be obstructed and for how long? And we make sure we set up our nurse as a priority resource, because that's the way we're going to get it to work. And we'll create a new entity generator that doesn't actually represent new entities coming in. Its sole purpose is just to grab and block this nurse for an amount of time, every X amount of time, which represents our frequency. And then we need to remember to start that generator running alongside our arrivals generator. So I'm going to whiz through this very quickly because of time, and you will have a chance to have a look at this yourself. But basically, you'll see in this one here, the resource unavailability example, I've added in 2 values here. One says unavailability time, so 15 minutes. So when the nurse is unavailable, it will be for a 15-minute period. and I want you to do that every 2 hours, every 120 minutes. Now here I've just put fixed values. There's nothing stopping you putting variability around that. You could build in some variability, sample from a distribution if you so wanted. In fact, you could put in really complex logic where if the nurse, what happens if the nurse is late for their break? Does that mean they get a shorter break, or do they still get the 15 minutes? You can do either. Again, you can write anything, anything you like. But the key thing that we're going to change here is creating this new generator function. I just called it obstruct nurse because its sole purpose is just to remove the nurse from play, so they can't see the any other patients. And here I've just put in a little print statement so we can see what's happening. And the first thing it'll do is it'll pause, it'll time out this generator for the frequency, so it'll wait for 2 hours. Then, basically, it'll demand a nurse. And the way it demands a nurse is by saying, exactly as we had before, requesting the nurse, but I've set the priority to be this fixed value of -1. That's going to be lower than any of the priority values that I've got specified elsewhere. So if I use a negative value, assuming I haven't used negative values in my patient priorities, then this will get the highest priority. And so now it's worth flagging up, key thing here, the nurse won't immediately start. If the nurse is with an entity at the moment, they're frozen in place, they are not available. So this will have to wait. So they will wait until the end of the current patient before they go on the break, which I would argue in most cases is probably true. I don't think the nurse would just get up halfway through seeing someone and say, well, I'm on my break now. So just be aware that that's how it works. That also means that it won't be exactly every 2 hours on the dot that you'll have a 15-minute break, even though I've got fixed values here, because the nurse may well be with someone, so their break may not start on time. But basically all it does, it grabs that nurse, and then it just times out with that nurse. That's all it does. So it uses the same kind of structure as a patient. It's just rather than using any entity, it just demands a nurse and freezes that nurse in place for an amount of time. Now I'm not going to go through all of the other bits as well, but just to say, and we have to start up that generator in the same way we start up the arrivals generator too. But basically that's all we do, and we could end up with quite a few of these if we wanted to block different resources for different amounts of time. Now, my advice would be don't get too bogged down with this. Don't get down into the level of, well, sometimes the nurse goes off for 5 minutes or whatever. Really, you want to be capturing a level of detail where you're saying, well, it is a known issue that we don't always have the doctor available. The doctor's only available for 50 minutes of an hour or whatever. This is a way you can model that. So if I run this very quickly, just so you can see how this works, you'll see with the print statements. Again, I've just put the print statements in so you can see it. You won't need that for a final model. First thing, the nurse will go on a break around, and I've put around time 120 because it won't be on the dot unless they don't have a patient there. And in fact, they weren't far behind that. So the nurse ended up going on a break for 15 minutes, and they were back at time 135.656. So that means that they actually were with a patient at time 120, but at time point 120.6566, they were free. So they were nearly free. But if you read that down through, you can see that happens. And it goes back to this point. Remember, time units aren't just integers in SimPy. You get these floating points as well. Okay, so that's resource unavailability. I'm gonna scoot us on unless there's anything urgent, Sammy, that's come up about that.
No, I think we can come back to some of these questions a bit later. So I will keep.
I'm just conscious that I've got a few more things to go through, and I want to make sure everybody's got time to you will have time to explore this. You've got a nice big exercise this morning, and I want to give you the time to do that. First thing we're going to cover next is about the Lognormal distribution. Lognormal, if you remember in the first session of discrete event simulation, we talked about how at the start of when we build a discrete event simulation initially, we tend to make everything, just for simplicity, we sample from an exponential distribution for everything. But when in reality, exponential distributions are really good for our inter-arrival times, and something called a log-normal distribution is actually typically a better fit for activity time. So the amount of time you spend with a nurse, the amount of time you spend being registered, all that kind of stuff. Okay. So we said we'll start with exponential, just make everything exponential, which is what you've been doing so far. You just use exponential distributions for everything. That makes it easy because an exponential distribution, all you have to give is, well, it's lambda, but lambda is just 1 over the mean. So it's really easy to say, as you're building up the model with your stakeholders, say, is that about right? Every three, they spend about 3 minutes with the nurse, yeah, and they'll say, no, it's about 5 minutes actually, and you just change that. It makes it very easy to tweak those things. But at some point, we will want to transfer over to log-normal distributions. And as I say, log-normal distributions are commonly used in discrete event simulations to model the time for a task to be performed. Now, a log-normal distribution is right skewed, which basically just means that it's got this long tail that you see here. So in non-mathematical terms, that basically means that if you use a log-normal distribution for an activity time, it says that most activity times will be pretty similar, but some will be a bit longer, and there'll be a few that are much longer. Okay, now that tends to represent patient pathway activities really well, and if you think about that, it kind of makes sense. You say, well, most things will work around. There'll be a little bit of variability, but we are going to get the odd thing where things go really wrong, and it's going to take much longer. And so that's why log-normal distributions work so well. Now, there's a really nice link here to a Towards Data Science article that's got a really nice, and I would say fairly simple explanation of how a log-normal distribution works. So if you're interested in that, you don't need to read that. You don't need to understand the mathematics behind it. But if you do want to get a bit more understanding about it, that's a nice little way to get introduced. It's fairly friendly. But really, as a modeler, the key thing you need to know is that log normals are typically good for activity times, and exponentials are typically good for inter-arrival times. Okay. So let's just remind ourselves a little bit about, because you need to know a little something now in order to use log-normal distributions. So in order to do that, we're going to need to remind ourselves of logarithms, which probably many of us learned at school and then completely forgot. But logarithms are basically the opposite of an exponential. And this is from this link here. This is a super simple explanation made for young children, and therefore is exactly at the level I like. And this, I think, is a really elegant description of a logarithm. It's basically how many of one number do you need to multiply together to make another number. That's fundamentally what a logarithm is. So as an example here, how many 2's multiply together to make 8? Well, the answer is 3, because it's 2 times 2 times 2. We have to multiply 2 3 times to get to itself to get the value 8. So logarithm logarithm base 2 of the value 8 gives us a result of 3. Okay, and that's all a logarithm is. Now, a log-normal distribution is one in which the logarithm of the random variable that we're sampling, so the random one that we're picking, just as we did for an exponential distribution, that random variable is itself normally distributed. Right. Just take a deep breath. This is gonna get a little bit messy. I'm not gonna go too much into this. You don't need to understand all the details of this. This is just to give you the basic gist of it, and then I'll tell you why you don't have to worry about it too much. Okay. So a normal distribution, not a log normal, but a normal distribution is basically a bell-shaped curve. This is what a normal distribution looks like, and it's symmetrical about its mean. Okay, and basically we define a normal distribution by 2 parameters that are known as mu and sigma. And mu basically is just the mean, and sigma is the standard deviation. Now, that means normal distributions are really easy to work with, because we can just say, let's say we were using a normal distribution to represent nurse time with nurse. we'd simply say, well, on average, they spend 6 minutes with a nurse and the standard deviation is 2. And we could just plug that straight in to a normal distribution and we could then use that. Okay. Unfortunately, though, normal distributions are not that useful for what we're doing. So we'll come back to that in a second. Now, a log normal distribution is basically a distribution which represents a random variable where the logarithm is normally distributed. So the mu and sigma of a log normal distribution do not represent the mean and standard deviation. What they actually represent are two things known as the location and scale of the distribution. They do represent the mean and standard deviation once the log normal distribution has been transformed using logarithms. So this gets a little bit complicated. Right, so this is basically what you need to know. You can really easily get mean and standard deviation from your data. So if you're looking at, activity times for seeing the nurse, you should be able to pull out from your data things like mean and standard deviation. So you want to be able to plug that into your model, okay? Now, if we used a normal distribution to represent an activity time, we could do that and it would be really easy. But the problem is the normal distribution isn't good for activity times. I mean, for starters, because it's symmetrical, it allows negative values. So you can end up sampling that you spent minus 6 minutes with a nurse. That's completely nonsensical. So we can't use a normal distribution, okay? And if we try and chop it off, we're not going to get the benefit of the distribution. So instead, we need to use a log normal distribution, but we can't give a log normal distribution the mean and standard deviation directly from our data, because in a log normal distribution, the mean and standard deviation of our data is actually represented in the underlying normal distribution, which is from the logarithms of the values that we're sampling. Remember, it's in a log normal distribution, it is the logarithms of the values in that graph. So the logarithms of these values are actually normally distributed like this. That's why we can't just give it, we can't just say, give me a log normal distribution with this mean and standard deviation. So what do we need to do? Because we want to be able to use these values, because that's useful for us and easy for us, but we can't use a normal distribution, we want to use a log normal. So what do we need to do? We basically need to convert our mean and standard deviation values into a mu and sigma that we can use for a log normal distribution. That's the main bit you need to understand. Now, meet Tom. So this is my colleague Tom. I've worked for Tom for many years. Tom and I were the Pencore team, basically, with Martin, who set it up back in 2011. Tom is an associate professor of health data science at the University of Exeter. And Tom, we like Tom because Tom has written a little Python class that allows you to just plug in your mean and standard deviation and it'll convert it for you. Okay, here is the piece of code that allows you to do it. It has been supplied to you. You can use it, and all you have to do. I'm not going to go through the details of how it works. You can read it. It's fairly straightforward-ish. This is the mathematics bit, how you do the conversion. But hopefully you can see how it works in principle. All you need to do is pop that file in the same directory as your model, and then import it, and then when we want to use a log normal distribution, we can simply create an instance of this log normal and call the sample method, and we give it the mean and standard deviation. It will then convert that, create a log normal distribution with those converted values, and then give us back the value we need. Tom's done it all for us. There we go. I'm not going to go through the example of that, but you can have a look. I'm just going to talk through these things now. You can check these bits of code out yourself. And again, it's in the logn example.py, and you've also got a lognormal.py, which is Tom's code, and you can see how this works in a real model. And I converted the time with nurse into lognormal distribution. I'm just going to rattle through these very quickly before we get into the exercise. You'll remember that we talked about reneging, balking, and jockeying as being queuing behaviours in the very first session. We said that basically not all queues run as planned, and sometimes they'll have reneging, which is where entities wait in the queue and then they basically give up waiting, or they are removed from the queue because they're no longer viable. So if your entity is like a test result and it's no longer useful, then it can be removed from the queue. Balking is where you never join the queue in the first place, either because you don't like the look of the length of the queue or because you can't because there's no capacity. And jockeying is where you switch queues, like at the supermarket. So for reneging, the way in which we do this in SimPy, we could imagine that each of our patients in our model has a patience level. So as well as a priority attribute, they've got a patience attribute, and that basically can represent the amount of time that they're prepared to wait for the nurse. Now, we've only got one activity here. You might, depending on your model, have different patient levels for different queues. They may be more patient for certain bits of the system than others. Depends how complex you want to make your model. But in very simple terms, that's all we need to do. Add in this patience attribute with some way of determining what the patient's patience is. Again, in the example I've put in and provided you with, it just randomly generates a patience level, but you probably in reality want to do something a bit more, a bit better than that. Then basically, when we request a resource, I'll show you this bit of it in a second. We basically, when we request the nurse, we say, okay, give me that request, or wait until the patience has run out. Okay, that's the bit of code I will just flag up in a moment. Then we basically check what happened and say, okay, did the patient wait for the nurse or did they walk out? If they walked out, then we make sure that they then don't see the nurse, and we'll record that they reneged. If they did wait, then we proceed as normal, and then we can add the number of patients that reneged to our results and take average results. And a lot of the changes you'll see in this are actually related to adding in extra columns of the data frame, recording how many reneged and all that kind of stuff. But the key bit I'm just going to very quickly show you now, because you can have a look at this in full yourselves. Sorry, that's the Lognormal one. So reneging example. The key bit I want to show you, because this is a bit different, is this bit here. So this is where we request the nurse. Remember, we call that request REQ. This is normally where we say yield REQ. And that basically means freeze in place until the request can be met. Here, what we're doing is we're saying yield the request, or, and this pipe symbol means or, timeout for the amount of time that is in the patience level for that particular patient. Okay, just like the priority was an attribute of the patient, here we've got the patience level, is how long they're prepared to wait for the nurse. And then we'll store that in a variable that I've called result of queue. So one of these two things will happen, and whichever one happens first will be the one that's stored here. Either the request will be met and REQ will be stored in result of queue, or this timeout will happen first. If the patient waits for the nurse, then this REQ, our request for the nurse, will be in this. So we can just do a simple if statement that says if REQ in result of queue. If that's true, that means this request was for the resource was met, and therefore they waited. So we know then the patient waited, and we proceed as before. If that isn't in there, that means it timed out before that request could be met. In other words, the patient ran out of patience, and so instead I'm just going to record that the patient reneged, and I'll print a little message there. Okay, but this is the key. There's other stuff in here that you'll want to look at, but the key. This is the key change that you're basically saying. I need you to do this or this, and whichever one happens first will get stored in here, and then we check what happened and we proceed based on what happened. Okay. I'm going to rattle through these very quickly. Balking, as we mentioned before, is balking. There are basically two ways in which that can happen, and you could have both that happen in the same model. You might have an entity that chooses not to join a queue because they don't want to, because they think it's too long, or it might be that they can't join the queue because there's no capacity for them to join the queue. The queue is in some way full. Now, in the example that I provide to you, I look at the latter way, that there's no capacity, but the principle is exactly the same. You can use it to emulate either of these. The only difference is that if it's in the former, this is a bit like reneging. You're basically saying that a patient has an attribute that would probably be something like their maximum queue length that they'd be prepared to have, and so you would check the length of the queue, and you would see whether it exceeds the maximum queue length they're willing to tolerate. But the way we've done it here is to say there's a global level parameter that says the maximum length of the queue for the nurse is this, and therefore any patient cannot join if it's beyond that. So the principle's the same. It's just if you were doing it this way, modelling it in that way, then it's kind of an attribute of the patient. An individual patient has a kind of tolerance for how long the queue can be, whereas this is an attribute of the model. It's a kind of global parameter, because it's saying, well, this is how many patients can join the queue physically. And the way we're going to basically do this is the crucial thing here is that we're going to have a list of patient objects that are currently in a queue at any one time. And I'm going to very quickly just show you this, and I'd encourage you to check this out, because it's a useful thing to do anyway, because it allows you to track which patients are in a queue at any one time. So there's lots of bits that you'll want to look at, but if I just scroll over to that bit. So here, where we set up the constructor for the model, you see I've set up an empty queue. So when we create a new model, I've set up this, basically a list that I've just called queue for nurse consult. And that list will store at any one time the patients that are waiting to see the nurse. Then all we basically do is whenever a patient joins the queue, or whenever it leaves the queue, we simply add that patient, append it, in the same way we append any item to a list. We append that patient to the list when they start queuing, and then remove the patient when they've stopped queuing. And the advantage of that is that at any point, we can access that queue for the nurse consult and see who's in the queue. So here, in this example, we use that so that we first check whenever any patient goes to join the queue, we check, is the length of the queue less than what we specified as being the maximum capacity for that queue. If you were doing that from the patient perspective, say that this patient won't queue if there's more than 10 people, then you could do that. You could do exactly the same thing, but just say we would attribute the patient. Is the current queue less than their tolerance level, if you like? But I'll let you look through all this. But the key thing is that this is a really useful thing to do, to store, regardless of whether you're doing reneging and balking, but actually just having a little list that you add a patient to it. So you have a list for each queue in your model, add a patient to it when they join the queue, remove them from it when they leave the queue, can be quite useful, because that means that you can then, of course, track your queue lengths over time. And the balking example with graph shows you exactly that, and it uses matplotlib, and I'll just run that very quickly for you, so you can see how that works. And you're probably already imagining that you can do that. So here we've only got one queue, but I've been able to track the length of that queue over time and plot it, which is probably quite a useful thing, depending on what you're trying to do. So it's a really easy way to do it. You can just say anytime that they join the queue, add them to the queue. You can always then check how many people are in the queue, but it also means you can track these queues over time as well. The last bit I was going to mention was about jockeying. Um, the key thing I'm going to mention about jockeying is that in 13 years of doing healthcare modelling, I have never once used jockeying in a model of a healthcare system. I don't believe that true jockeying comes up very often in the kind of models you'll be building. Um, uh, I think there are situations that are a little bit jockeying like, for example, where a patient might pick which queue to join in the first place. You could imagine if you were building a model where you have patients choosing which minor injury unit to go to or which emergency department based on times that are published. That is kind of like a jockeying behaviour, but true jockeying is really where they join one queue and then they skip over to another. You may have situations where that happens. If if you do, you're a little bit on your own because SimPy helpful. It must be complicated to do it in SimPy because SimPy won't even tell you how to do it. It acknowledges that it's a bit complicated and then just doesn't tell you how to do it. Fundamentally, though, you'd need to think about how you would do it and how the behaviour would work in your particular model, and you'd need some sort of behavioural model that would determine that a patient is likely to jockey and under which circumstances they're likely to jockey, and then you need to be able to remove them from one queue and place them in another, and that's where it gets a little bit more complicated because you'll need to suspend that request and start them with another. It can get a little bit more involved. My advice is I don't think you'll need it, but I have given you this kind of choosing queues version of jockeying where they choose which queue to join in the first place. And you can see that in the choose queue example where I've basically created the same version of this model with a nurse, but I've also said, well, they can basically choose between a nurse or a doctor, and they'll always go with a nurse if there's capacity, otherwise they'll go to the doctor. And that's basically, if you want to use that kind of approach, you could do that fairly simply. Okay. Apologies, I rattled through some of that, but I wanted to spend more of the time on the things that you are going to be using much more, which will be things like warm-up periods, priority-based queuing, resource unavailability, and log-normal distributions. Those are the big four, really, that you're going to use. But you may well use a bit of reneging and balking in particular, depending on what you're trying to do. So if you do want to have a look at those, and obviously I skipped over the log-normal a little bit quickly. So you've got all of those examples in the lecture examples, so I'd encourage you to have a look at that. But basically, I've sort of talked you through how it would work, and you can see in the code, just following the hashtag new to see what new bits have been added. Sammy, are there any sort of vital questions that have come up in this that haven't been answered?
There's a couple of really good questions, but I think if we respond to them in potentially the class tannoy or the central plaza, that might be better just for now. There's some very interesting ones. I also just wanted to mention a couple of quick things based on things that have come up. Appointment booking models. So if you've got a community service where you have repeated bookings for, seeing the same clinician, that sort of thing, we do cover this a little bit in the book. And there's also some code examples that I'll share a bit more widely afterwards, but do have a look in the chat if that's something you're interested in. The book also covers a package that allows you to import all of Tom's classes. So where we talked about the Lognormal class, he's got them all wrapped up into a nice package called SimTools that will allow you to import all those different Lognormal classes, and his version of the exponential distribution, etc. The other nice thing about those is that they make it very easy to control the variability. So it uses this random seed. And again, the book covers a little bit more on how to make your models potentially reproducible across different runs. So you can have the same variability within each run, but different variability across a whole trial. And that means that you can then start to vary parameters and be sure that you're seeing the same situation each time. And just then you can be sure that your parameter change is what is causing that new variability. And the final one, I just wanted to mention that pipe method that Dan showed. So waiting for the first of two possible times to elapse. that is such a powerful feature, and you will find that very useful for lots of different things. So that's one way you could do that, increasing priority over time, for example. It might not be the most efficient way, but it is actually one way you could definitely do that. Go wait until 3 hours has passed. Okay, if 3 hours passes before they get a nurse, bump their priority up, and so on and so forth. So that's definitely worth keeping in mind if you're ever thinking, if you're ever a bit stuck on how to do something, that pipe might actually be what you're looking for.
Yeah, that's a really good point. I hadn't thought about that actually. Yeah, that would be one way to approach that particularly for that sort of situation. Brilliant, thank you, Sammy. And yeah, apologies if we've missed any questions. We will get to them. My overall, there's a lot. I mean, it's great to see so many questions, and I can see there are lots of thoughts and ideas buzzing in your heads, which is great. This is the whole purpose of doing this. The overall answer to most of these questions is going to be yes, you can. You can do anything you like, and you can get quite creative about how you approach this stuff. So use this as a kind of starting point, but as I say, Sammy's materials as well in that book will go over this plus more, plus an easier way to access Tom's stuff, a bit more of an elegant way, plus lots of other useful stuff that he's done. So do use that as a resource. This is a continual sort of learning thing. You will be learning new things as you go, in terms of how you do this, and in terms of how you encounter a new problem. You think, oh, how will I model that little quirk in my discrete event simulation? So we're kind of giving you the basics of SimPy plus the thing that these things in here, which are going to crop up a lot, which are you're probably going to need a warm-up period for a lot of your models. You'll probably have some sort of priority-based queuing somewhere. You'll probably need to model something about resource unavailability, and you're going to want to use log-normal distributions. So those four, I'd say, are the key four extras for basic models. But there's so much more that you can do. Okay, let's break there because I want to make sure that people have got time for this exercise. So I'm going to suggest that was a long lecture. Apologies for that. I think next year we're going to have to, the same thing happened with the last one, I think we'd have to extend out the discrete event simulation module. There's so much that gets packed into it, but hopefully it's been useful for you. What we're going to do now, go on a break for 10 minutes. Then you're going to go into your groups, and basically what I want you to do as a group is to build or design and build a discrete event simulation model that uses at least 4 of these features. Any 4 you like, but uses at least 4 of these. You can use all 8 if you so choose. The model can be of anything you like. Okay, so you're just going to design your own discrete event simulation and build it that has some of these features in it too. Now you could choose the in session 2A. You all designed in your groups a discrete event simulation. You could put that into practice and build it. I will say be careful, because I know at least I think 6 of the groups came up with this theme park idea. It was really interesting. That you probably need to use something known as the governor approach, which we've mentioned but haven't shown you. So I probably wouldn't do the theme park thing unless you're going to make it a very linear system. Otherwise, you'll have a steep learning curve to try and pick up that extra way of doing things. So it's up to you, and I don't want to tell you what to do. So I want you as a group to decide how you're going to approach this. But if you did come up with that and you're not feeling confident about going off and learning another thing on top, and then putting it into practice, you may want to just choose something different. We're basically going to give you, I want to give you as much time as possible. So the original plan was to give you an hour and a half and then get people to present. I think what we may do, because we're going to have some PSG points awarded. I think it's more important we give you the time to build the model. So I think if we go till 25 past 12, and we'll ask people to each group to share their model on their Slack channel. Sammy, if you're happy to have a look at those either over lunch or whenever, and then make some judgment, would you be happy to do that? And then it'll maximise the time for people to build them.
Yeah, that sounds good to me.
Okay, great, thank you. So yeah, Sammy will come up with some judgments, and to make sure we don't overrun, because Sammy's got lots to get through this afternoon as well. Okay, I'll stop there. I will open up the breakout rooms, but go and have a break first because that was a lot of information again to take in. And some of this you'll need to go back and have a little look at the code. But in your groups, first of all, just have a chat about what you're going to do and come up with anything. Be as creative as you like. And I'm looking forward to seeing some really interesting takes. You may do something we haven't even talked about here. However you like to approach this. Be creative. A lot of model building is creativity as well. Okay, go and have a break and then assemble in your groups. Hi everyone, welcome back. So I just wanted to give you an extra few minutes. I knew there were quite a few groups that were just needing a little bit of extra time. But I managed to get around to most of the groups. Absolutely amazed by what you've all done. Genuinely, I walked into every group, and the creativity of the stuff you designed, but also the fantastic way you really grasped hold of the SimPy approach and really sort of understanding it. Really fantastic, absolutely amazing to see the models you've developed and are continuing to develop. So. Obviously, post your model code. Remember to don't drop it in as just copying and pasting code. If you take the Py file, drag and drop the Py file into Slack. That'll allow Sammy to then open up the Py file. It may also be helpful just to put a very brief sort of 2 or 3 sentence description of your model as well, just to so Sammy can see what you've done. So I think with Sammy teaching this afternoon and also running the revision session tomorrow, she's going to hope to get to look at all these by the end of tomorrow. But there will be some PSG points awarded. And I think Sammy's going to award some ad hoc points and some of the things that she's seen as she's floated around as well. Because yeah, absolutely amazing seeing what you've all done. Really, really good work and picking up these skills. This is a lot of you, I suspect, will go on to do discrete event simulations in your projects. Or even beyond that, and so it's great that you've managed to pick up those skills so well, and I can't wait to see what you come up with for project ideas, and hopefully you've enjoyed this module as an introduction to pathway modelling and see what you can do. SimPy's got a steep learning curve, but once you get the hang of it, hopefully what you've seen is that the structure's always the same, and then you can just build things on, bolt on little bits, change little bits here and there, and you can pretty much do anything. It's a really creative way of modelling. Sammy, just before we close for lunch, anything you wanted to add on that?
No, that's all good. I guess the one thing I will say is if there's any small bugs, etc., if it's not running, and I saw one group that were rushing to try and get something fixed. If there's any small bugs, I will debug it and try and get it running. Just so I can properly assess how it's gone. So don't panic. I'll be looking at what you were attempting to do, even if the code isn't quite working yet. So.
Yeah, no, absolutely. I mean, don't worry too much about that. I mean, it's you had basically an hour and 20 minutes to come up with a design and then build a discrete event simulation model. Your project work will be doing that basically. If you're doing a discrete event project, so in the time you had, that's absolutely incredible. What you come up with, so don't worry too much about those small little things. The other thing I was going to flag up as well. Great to see such collaboration going on in the groups. Just a reminder: do make sure that you're alternating between people who are sharing the screens. If I would again encourage you as much as possible, if you are struggling. Do volunteer to share your screen. I know it seems counterintuitive to do that, but we've seen some groups. I'll name drop TIA as well. Again, really good at doing that to make sure, because actually, if you're struggling, the best thing to do is get everyone helping you, and so you are then controlling the speed. And also, I have to shout out to RJ McCall. I got in there about 20 minutes ago. Absolutely amazing what you were doing. Fantastic. Great to see such collaborative work, and you were really developing some fantastic code there. So really well done to all of you. Okay, I'll stop talking there and let you go to lunch. So we'll resume at 1:30, and you'll be delighted to hear you won't hear my droning voice now, but Sammy will take you on the world of geographic modelling. You'll also be extra delighted to know there's no Python this afternoon, so it's all drag and drop, and Sammy will show you the wonders of QGIS, which is not Python based. You get a bit of a break from Python this afternoon.